So we're going to accomplish a few things today. We're going to start off with a special application that applies to construction. It's a calculation you don't see very often. And what we're looking at is a circular dormer. Now we're sticking to a flat surface, so we're looking at a surface, regular gabled roof, but coming off of that roof, we have a circular dormer. So the way that dormer intersects the roof, and two things that we look at is the volume of the roof itself, the volume of the dormer itself, I should say, and then the area of the outside of the dormer. And we'll look at how all that stuff gets calculated and special formulas for it. Now, the first thing I want to start out with is the volume of the dormer. So we're just looking at the volume of that portion. So think of this as being a right triangle here. The round portion here, and then of course that coming up like that. Oops, get back up there. So something similar to that. There are only a few dimensions, actually only two dimensions that we can measure about this dormer. One is the radius of the circle here. This is a true half circle. This formula only applies if this is a true half circle. L, which is the ridge length, so from the main roof out to the top of that circle is L. So those are the only two things that describe the dormer. The third piece of information here is N, which is the slope of the main roof. So that's the slope of the main roof over here. That's N. And of course, all that determines is what we're cutting off here. Now, if this were a full cylinder, so a first full circle here coming up to a point and being cut off like that, well, what we would do is we would either find the volume of the whole cylinder and divide it by 2 because it's a half of a cylinder, or we would use, like we did yesterday with the chimney, we would use an average height. If this length here is L, that would be equivalent to the height of the cylinder. We would just take the area of the circle, and for volume, we would just take that area of that circle times L over 2, because that's the average height. On this side, the height is 0, because it cuts all the way down to the circle. On this height, on that side, the full height is L. So it's area of the base times the average height. However, here it's not a full circle. It's only half a circle. And because it's only half a circle, when we run this up here, so that would be the full shape. We would have the area of this half circle times L would give us the volume of that full shape. But this is cut off like this. And because it's cut off like that, you'll notice this piece here that is removed is the larger of the two pieces. So what we have left here is way less than half of that full the full solid that we had before with that half circle. So we can't just find the area times an average height because we're not truly cutting it in half the way we're doing that. We're cutting out a bigger piece. Kind of like when we cut a wedge to create a pyramid, we're cutting off the smaller piece. Here we're cutting off the larger piece. So the reason I'm showing you these things is to establish that there is not a simple way that we can derive this formula with just using our basic knowledge and cutting things up and putting them back together. So this does require going into calculus. Now, I'm not going to show you the calculus. I'm just going to show you the formulas behind it. But if we are told, if we know or given the radius of the dormer, remember that's R, and the slope of the main roof. Now remember, we're not using S for slope here, we're using N for slope. So in other words, here's our dormer. Let's say we're being told that this has a radius of 8 feet. And that our main roof back here has a slope of, let's go 612. The formula for volume of that dormer is 8 times the radius, I should use little r for radius, 8 times the radius cubed over n. So the volume of this dormer here is going to be 8 times that radius of 8 cubed over n, which is 612. Notice we just put in the 6 there. So 8 times 8 cubed divided by 6 gives us 682.67. Now the units, this radius was given in feet. So this unit's going to be in cubic foot. Notice that is the only dimension here. The radius is in feet. The 8 is a constant. N is a slope. There's no units on the slope for that 612 slope. So that the feet is the only unit in this calculation. Well, the second method that could be used for finding the volume of the dormer would be to be given the ridge length. That's what we had called L. And the radius of the dormer. That would be R. This would give you something a little more familiar, a little more similar to the area of a base divided by, or times the height, divided up. So for this example, let's say we have a radius here of 6 feet. And instead of having the slope of the main roof, we're told that this length up here, well, let's say that it's 12 feet. So our volume formula based off of that information, 2/3 times L times R squared. So for this information, it'll be 2/3 times L is 12 times 6 squared. So 2 divided by 3, times 12 times 6 squared gives us 288 cubic feet. Now we could test this to make sure that these formulas give us the same. This radius of 6, of course, would be vertical as well, and that length of 12 would technically be a run of a slope. So this is a 612 roof. So let's make sure that that formula for radius and slope gives us the same result. So that formula was 8 times the radius cubed. So that'd be 8 times 6 cubed over 6. 8 times 6 to the power of 3 and divided by 6 is also 288 cubic feet. So we do get the same area, or same volume, I should say, for that dormer, no matter which two pieces of information we use and to find that volume. Now, I did not give you a formula for the volume of that dormer if all we're given is the length of the ridge and the slope. The length of the ridge R and the slope of the main roof N. There's our circle for our dormer. So let's say that I tell you that this is 24 feet here. And the slope of my main roof, let's call it let's go 812 slope. So what this is going to tell us here, we can actually find the radius of the circle by looking at that ridge. And then the vertical radius here, R, is going to form a right triangle there. If I draw that off, it's going to look like this. This is R, that's the length of the ridge. Well, this is 24 feet. This side here goes up the slope of the main roof. That is going at that 812 slope. So it's going to be equivalent to this, 8 over 12 like that. So I can use a proportion to find R. 8 over 12, the slope of my roof, is equal to R, that radius, over L, the length of my ridge. So for this example, 8 over 12 equals R over 24. Tell us that radius in this case would have to be 16 feet. So I can find my volume one of two ways. I can use the radius and the length of the ridge, so that'd be 2/3 times the length of the ridge times the radius squared. 2 divided by 3 times 24 times 16 squared is 4,096 cubic feet. Or I could have used the formula 8 times the radius cubed over the slope of the roof, N. That would be 8 times 16 cubed over 8, which, if we calculate that out, is also 4,096 cubic feet. Now, volume we've got down here. We can find the volume. In fact, if we wanted to, we could create a new formula for when we are given the slope and the ridge length. In other words, N and L. Because we were able to find here that R, if I solve this for R, so it's N over 12 equals the radius over that ridge length. Cross multiply N times L and divide by 12, that equals R. So because R equals N times L over 12, I can use that now to work into my formula. I'm going to use the formula, the volume equals 8 times R cubed over N. So I'm going to put in this for R. This is going to be NL over 12 cubed over N. When I cube this, I have to cube each piece. So n cubed is n cubed. L cubed is L cubed. And this is over 12 cubed is 1,728 all over n. Well, I'm going to split this into two pieces here. I'm going to have the 8 over n times the n to the third L to the third over the 1,728. And I'm going to do a little cross canceling here. I'm going to cross cancel one of the n's. So this is now n squared. I'm also going to cross cancel the 8 and the 1728. 1,728 divides by 8 to give us 216. So what we have here is that the volume equals n squared, the slope of the main roof squared, times the length of that ridge cubed over 216. Ironically, not ironically, I suppose I shouldn't say, but interestingly, we would get the exact same formula if we had worked from the other volume formula. The volume formula, the volume of that is 2/3 times L times R squared. If I put in that expression for R, NL over 12 for R, this is 2/3 times L times N times L over 12 squared. The 2/3 L are going to stay as they are. In fact, I'm going to write that as 2L over 3. I'm going to multiply the 2 times the L. Treat that as an L over 1. And then times N squared is N squared. L squared is L squared. And 12 squared is 144. Now a little combining here. 2L times N squared L. Well, we've got the 2. Nothing multiplies the N squared. L times L squared is L cubed. 3 times 144 is 432. And if I divide out, I reduce by the 2 there, I get 1 and 216. So this is N squared L to the third over 216. Again, same formula. So if I wanted to find the area of this using just the slope of the main roof and the length of that ridge, there's the formula for it. Let's talk about surface area. Well, if I want to talk about the surface area of the end of this, well, this is just a half circle here, isn't it? So that surface area of the end is just the area of a circle, pi times r squared divided by 2, because it's half a circle. So if I have a radius here of 8 feet, the area of the end of this is pi times 8 squared over 2, which ends up being, I think, 100.96. 100.48, sorry, square feet. Well, again, the area of the side of it, which we'll refer to as the lateral area here, the lateral surface area, which is this area here, the part that would normally wrap around the cylinder, but it's cut off because of that roof. That area is the tough part to describe. Again, you could think of it as being like a fourth of the lateral surface area, but it doesn't quite work that way. Because again, if you're thinking of the lateral surface area, get out of there. The lateral surface area is this area that wraps around the cylinder. If I went from corner to corner, from here to here, I would be cutting that lateral surface area in half, but I didn't do that. I went from corner to side of the cylinder. So what I'm losing there is more than 3/4 of the lateral area of that cylinder, unfortunately. So let's take a look here at that area. The formula that we have for the area is 24 times the radius of the circle of that dormer cubed divided by n, which is the slope of the main roof. So let's say I have a radius here of 8 feet, cutting into a roof that is a 612 slope. So this area here is 24 times that radius of 8 cubed over n of 6. 24 times 8 cubed divided by 6. We get 2,048 square feet of area. Now, let's take a look at how this would be affected if I put L in here, the length of the ridge. Remember, we had that formula here, n over 12 equals r over L. If I wanted to solve this for, let's solve it for n so I can replace the n with L. I'm going to cross multiply. It's going to be 12 times r divided by L. So n equals 12r divided by L. So in my original formula up here, I'm going to replace n with 12r over L. Now I'm dividing by 12r over L. So what that means, I'm going to have my 24 times r cubed. I'm going to put that over 1, small r, and small r up here too. Screwing that up. Times the reciprocal of this. So it'll be L on top and 12r on bottom. And we notice 24 and 12 cancel. They both divide by 12 to give us 1 and 2. R cubed and r cancel out to give me just r squared. So this ends up being r squared, 2r squared times L is the area of that. You'll notice the one thing that is notably missing, and that is the pi. Where did the pi go? Well, pi ends up actually being the constant that we divide the regular lateral area by. Actually, pi over 2 is what comes into play. Actually, it's 2 pi, but anyway. Well, we end up dividing that regular lateral area by in order to reduce this down so that we can find that section of that lateral area. So the area could be thought of as 2 times the radius squared times the length of the ridge, instead of using this formula here. So if I'm given 6-foot radius, 12-foot ridge, that area is going to be 2 times 6 squared times 12. Gives a lateral area of 864 square feet. If we use the original formula, it would have been 24 times 6 cubed over 6 and radius is 6 and a ridge of 12. Actually also works out to be a 612 slope because this would be 6. That would be 12. That's where the 6 came from on the bottom there. The 24 times 6 cubed divided by 6 also gives us 864 square feet. So we can see those formulas are equivalent. This is an architectural feature that is not near as common as it used to be. Having a round gable so that you could actually have a round window up there used to be relatively common because they didn't want to mix triangles and half circles together. Now it's become way more acceptable to just do a triangular gable with your half circle window in it. So this calculation is not as important as it used to be, but I wanted to show it to you just because it's out there. Might be something you run into. It's interesting to know if nothing else. It doesn't hurt to know it, put it that way. So next we want to talk about what happens when we start mixing circles with straight lines in different ways. And one that we have not really discussed much in here, it's a huge machining application, a mechanical application, and it's a V-block. So here's what we have here. This V-block, I'm going to say that this has an angle in here. What do I want to put in there? I'm just going to call it 28 degrees for now. And I'm going to say this dimension here is 2 inches. And that this round piece here has a diameter of 6 inches. This height here is 6 inches. I want to know the dimension x here. How far does that stick out above the top of that block? To do this, we go back to that rule that tangents to a circle are perpendicular to the radius. They form a right angle with the radius. So I'm going to draw my radius. I can draw it in either direction, doesn't matter, or both. Those form right angles there. Now, if the diameter is 6, that means the radius is 3 inches. So I can label each of these 3 inches. One of the rules we saw with circles a couple of units ago when we did our circles was if I cut this like this, first, these two tangents, those two lengths, are going to be the same. If I cut it down like that, it's going to cut this angle down here in half. So this will be 14 degrees and 14 degrees. So what I have here is two triangles that are equivalent. Both of them are right triangles. Here's my right angle. I know this other angle is 14 degrees. I know this side is 3 inches. I can now find the length of this side. According to the 14 degrees, this is the opposite side. This is the hypotenuse. Opposite and hypotenuse make sine. So the sine of 14 degrees equals my opposite side of 3 inches over that hypotenuse. We'll put that over 1 so that we can cross multiply and divide. Well, 1 times 3 is 3, divided by the sine of 14 degrees. Gives us 12.40 inches. So this length right here, from here to here, is 12.40 inches. Well, now we can find x, because one of our strategies for finding a height, we need to know the height from here all the way up to find x. Well, one of our strategies for doing that is to find pieces. We have the 2 inches here. We now have the 12.4 inches here. And we have this radius of 3 inches there. We add those up, 12 plus 2 plus 12.40 gives us a total of 17.40 inches. Next, we're going to find that total height here in a different way. Well, that total height can be found by taking this 6 inches here plus x. So 17.40 equals 6 plus x. If we subtract the 6, we get 11.40 equals x. That's 11.40 inches. So now there's obviously some issues there because 12.40 inches is probably going to put this above the top of that V block. But the calculation, it would change the calculation some. But right now we're going to keep it simple. We're going to assume it stays within the V block. I gave you kind of bad dimensions. I should have had a bigger angle here than 28 degrees. Let's do a similar example of that. I should draw my circle in here first. So we're going to look at this here. What we have here is, let's say that this is 2 point, well, let's make it simple. Let's save the decimals and let's call this 24 inches up here. We'll call this piece here 3 inches. This angle here I'm going to call 68 degrees. Let's see here. I'm going to find this dimension here to be 40 inches. I think I've got enough information here. I want to find X if the radius or the diameter of this is 16 inches. So I want to find X, the distance from the edge of that round piece out to the very edge down there. So once again, we have a round piece sitting in tangents, touching tangents. So I'm going to draw my radius. So this radius will form a right angle there. This radius would form a right angle there to that tangent. We know the diameter of 16, we have a radius of 8. So each of those radii is 8 inches. We also know that if we cut this across here, it cuts that angle in half. So we have 34 degrees there. What we're really working with is this triangle, right triangle, 34 degrees, 8 inches over here. The piece that I want to know is I want to know this piece here. This piece. That is the adjacent side according to the 34 inches. 8 is the opposite side. Opposite and adjacent make the trig function tangent. Tangent of 34 degrees equals the opposite side of 8 over the adjacent side, which is what we're looking for. We'll put that over 1, and we will cross, multiply, and divide. Well, 1 times 8 is 8, divided by the tangent of 34 degrees. Gives us 11.86 inches. So this distance here is 11.86 inches. We know the distance from here to here is just the radius of our circle, which is 8 inches. What we don't know here, at least not yet, is this distance here. So I'm going to label that distance A. If I find that, then we can find X rather simply here by just subtracting those dimensions from 40. Find A. I look at this triangle, and I see that there is a piece of information I'm missing here. So let me fill it in here. I'm going to say this is 4 inches here. And that's 4, 3. Let's call this whole side over here is 20. Make it more reasonable. We'll call it 32 inches here. So what we have is we have 3 inches here and 4 inches there. That would be 3 inches and 4 inches. From here to here would have to be 25 inches. So this piece here, this side, is 25 inches. That's our right angle there. If this is 68 degrees, this angle here is 22 degrees. So I now have a right triangle there that is right angle there, 22 degrees. and 25 inches here. And I want to know this side up here. I'll call that B. Well, that side is the opposite side. 25 would be the adjacent leg. Those are the two legs because they both make the right angle. So we're dealing with a tangent. Tangent of 22 degrees equals that opposite side, which is what we're looking for. That's B. Over the adjacent side of 25 inches. We put that over 1 so that we can cross multiply and divide. So 25 times the tangent of 22 degrees divided by 1, which we don't really have to do, gives us 10.1 inch. So this is 10.10 inches. 24 minus 10.10 is 13.90 inches here. So we have 13.90 plus 11.86 plus 8, we'll go 8.00. That'll give us the distance from here over to the edge of the ball there. Which is 33.76. So this distance here is 40 minus the 33.76, giving us 6.24 inches. That's our dimension X. So using that idea that the radius of a circle is always perpendicular, always forms a right angle to the tangent, is a very powerful tool. These are called V-block applications in machining or mechanical design. It can happen in woods if you're looking at working with dowels. I know a lot of times they'll take like a clothes rod, they'll take a dowel and they'll flatten one side of it to make it set better. That is a matter of setting up that dowel in a V-block, actually similar to this, and then machining it or running it through a sander to take that edge off there and flatten that top edge. A mill is probably the best way of doing that, by the way. Let's look at another application. So our next application I want to look at is, let's take our regular polygon and pop it out into 3 dimensions. So what we're going to look at is we're going to look here at a octagon hut, basically. See if I can draw this out halfway is decent. And we're looking at the roof on that. Coming up to peaks like that. And we're going to find a couple of things. First, we're going to find what's called big R and little r. And this, of course, is from the center here. We're going to find h, the height here. Well, let's stick with that. No. We are, of course, going to find the roof area at some point. So pretend this is a regular octagon with 10-foot sides. If you recall, we can find the area of a regular polygon if L is the length of our side and N is the number of sides. That area is N times L squared over 4 times the tangent of 180 over N. So here that would be, N would be 8. That's 8 times 10 squared divided by 4. And then we're going to divide that by the tangent of 180 over 8 what is that, 22.5? So we're divided by the tangent of 22.5. Gives us 482.84. Square feet is the floor area of that hut. That would be just the area of that regular polygon. Now I want to find little r would be the distance from the center of that polygon out to the middle of one of the sides. This would be it's called little r because it's the radius of it would be the inscribed circle. The circle would be put on the inside of the polygon. It's also called the apothem of the figure. One way of finding, we could actually do a reverse calculation here. One way of finding the area of a figure like that is n times little r over, sorry, not n times little r, it's L times little r over 2 times n. L is the length of the side here. You can see that L times r over 2 would just be the area of that green triangle, times n because there's a triangle on each side of the figure. Well, I know that area is 482.84 square feet. I know that L is 10 feet, and I know that n is 8, so I need r over 2. So, well, 10 times 8 is 80 divided by 2, so that's 40r here. 482.84 equals 40r. So I just take that 482.84 and divide by 40 to solve for r. R is 12.07 feet here. Now, there are other ways I could have gone about that. I know that this angle here and this angle and all those interior angles are the same. We know the angle sum is n minus 2 times 180. So there's 8 sides, so n minus 2 is 6. So 180 times 6, I believe that's 1,040. 1,080, I should say, and it is 1,080 degrees. Divided by there are 8 of those angles. Divided by 8 gives us that 135 degrees is each of those angles. So if this angle is 135 degrees, when I cut it here to make this triangle, it cuts it in half, which makes that 67.5 degrees. So I can actually look at this triangle, which is half of that triangle, where this is 67.5 degrees. This is a right angle. This is that little r, and this is half of my side. This is L over 2. Since L is 10, this would be 5 feet. So r could be found using the tangent, 67.5 degrees, equals r over 5. Put that over 1, and I can cross multiply and divide. So 5 times the tangent of 67.5 degrees gives us 12.07. So we get that same length for r no matter how we go about finding it. So r is 12.07. Big R, then, is the distance from the center to one of the corners. That would be the large radius of what we call the circumscribed circle, a circle that went around the outside of the figure. It would be the larger radius. So let's find, come on now. The old pen's acting up today. There we go. So let's find big R. Well, big R comes from this right down here. If little r is 12.07 and this is 5, big R is just the hypotenuse of that triangle, so it's the square root of 12.07 squared plus 5 squared. Giving us 13.065 feet. So big R is 13.065 feet. So we've got little r and big R. To find h here, this height, we need to know a slope. So let's say I'm going to tell you that the slope on this is an 812 slope. Here's h. This is 812. The bottom of this is actually little r, 12.07 feet. Because if you look at it, little r is this one here. That would be what would be directly under the slanted surface going up to the peak. So we have 8 over 12 equals h over 12.07. Well, you can see this is just going to be a little bit more than 8 here. H, not 8 here. We're going to cross multiply and divide. 8 times 12.07 divided by 12 is 8.05. Now, 8.0466666, it's actually like 8 1/24, I believe, of a inch. We're okay with just leaving it as 8.05 for now. Feet, their height. To find the area, then, I would want to find the slant length going up one of these. I'm going to call that J. That's my common rafter length from what we were doing at the beginning of the semester. And J is just the hypotenuse of this triangle. So that's going to be the square root of 12.07 squared plus h of 8.05 squared. Giving us that length of 14.508 feet. So now we are ready to find the roof area of this. The roof area is made up of 8 triangles here that are 10 feet on the bottom. That's just the length of the side. This is 10 feet here, the length of the side of that. And a height of that 14.508 that we just found. So to find the area of an individual one of those triangles, it's 10 feet times 14.508 feet divided by 2. 1. Giving us 72.54 square feet. But now that's an 8-sided roof, so there's 8 of those. So times 8. Giving us 580.32 square feet of roof area. So that is all of our dimensions that we would need for that piece. Finding the volume of that roof would now be a little bit trickier. It is just a pyramid. We know the area of the base. We found that up here. The floor area, 482.84. Square feet of area. We found the height was the 8.05 feet here. The volume of a pyramid as long as it comes to a point, it doesn't matter how many sides it has, that volume is the area of the base times the height divided by 3. Here it'll be the 482.84 square feet times the height of 8.05 feet divided by 3. There's my sharing got screwed up just a second here. There, we're back. So 482.84 times 8.05 divided by 3. We have 1295.62. And that'll be cubic feet is the volume of the roof. That's just from the top of the walls up to the peak. So this is all stuff we've seen before, just applied in slightly different shapes. For your use, I put a worksheet out there, or for your homework, I should say, there's a worksheet out there dealing with some of the examples we've done today. There's also a greenhouse roof example out there that I did not get to today, but I want to make sure you guys have time here. So the homework, there's a new worksheet out there that is labeled Worksheet 4-29. There are 2 quizzes out there that you need to finish up and turn into me. If you didn't notice, there's quiz 425. I went over every problem using the same numbers on quiz 425 last Thursday in class. Last Thursday's lecture, the example problems that I did were the questions off of quiz 425. Then there's quiz 426. Those were actually the exact example problems I used yesterday. At the beginning of the lecture. So if you go back through those videos, you should be able to finish up those quizzes. If you have any questions, let me know. So I'm going to let you guys have the last, you have break coming up here, now you have about 40 minutes of class left. I'll let you guys have that last 40 minutes to get working on stuff. Also remember, this is a big one, the final test is posted out there in Blackboard for you. I highly recommend you get started on that. We are going to work on it in class all of next week, but it's a tough one. I mean, obviously these last 2 quizzes were bad enough in themselves. This test includes those last 2 quizzes plus some other stuff from earlier in the course. So I highly recommend that you get started on it. Put it that way. It's going to take a while to finish that up. We will discuss those more next week. Remember, this Thursday you guys are with Scott, so I'm taking some personal time so that I won't be here for class on Thursday. So you guys enjoy. I can't remember now what it was that Scott has planned for you, but you guys enjoy that, and we'll see you all on Monday.